U.S. Navy pilot faced every aviator's worst nightmare when an arresting cable snapped during a landing on an aircraft carrier, leaving everyone on board horrified. On an aircraft carrier, planes land at high speeds, using tail hooks to catch a cable that stops them from going off the deck into the sea. While these landings look amazing and swift, they require precise timing and equipment, making them highly risky. But what exactly happens when the arresting cable fails? Can casualties be minimized in such incidents? Join us as we explore the shocking details of what happened after a U.S. Navy pilot broke brakes, arresting cable on an aircraft carrier. On March 18, 2016, one of the United States aircraft carriers, the USS Dwight D. Eisenhower, was carrying out routine flight operations about 100 nautical miles from Norfolk, Virginia. The weather was perfect for carrier operations. Around 2 p.m. local time, an E-2C Hawkeye from Airborne Early Warning Squadron 123, call sign Screw-Top 601, approached the carrier to land. That day, 3 Hawkeyes from Carrier Airborne Early Warning Squadron 123 were practicing landings off the coast of Virginia. One of the planes, despite making a perfect landing and hooking the fourth and final arresting cable, didn't slow down. The Hawkeye, an important part of the carrier's air wing with its rotating radar dome, had just finished a regular 5-hour surveillance mission. As the plane came in for landing, everything seemed normal. The landing signal officers on the carrier's deck gave the command, signaling that the pilot had visual contact with the landing system. The Hawkeye's speed and angle were correct as it approached the ship, but when the plane's tailhook caught the number 4 wire, disaster struck. With a loud noise that sounded like a mix of a gunshot and a metallic screech, the arresting cable snapped. In an instant, the landing turned into a deadly scenario. The Hawkeye, now with no way to slow down, kept speeding down the flight deck. The deck crew, trained for emergencies like this, quickly hit the deck to avoid being hit by the recoiling cable. The safe recovery of Screw-Top 601 showed the effectiveness of naval aviator training and the strength of naval aircraft design. It also emphasized the need for multiple carriers to be nearby for emergencies. The Navy later blamed poor maintenance for the rare incident that injured 8 sailors and almost sent the Hawkeye into the ocean. The plane briefly disappeared as the pilots struggled to regain control, coming within 20 feet of hitting the water. While the Hawkeye and its crew were unharmed, the incident left behind injuries and damage on the Eisenhower's flight deck. The recoiling cable caused injuries to 8 sailors, with the most serious being a sailor who suffered a skull fracture when the cable struck his helmet with such force that it cracked. The 30-second event led to 6 medical evacuations and caused over $200,000 in damage to the carrier and aircraft on deck. The damage was blamed on complicated maintenance procedures and mistakes by the crew. Medical teams on the carrier acted quickly, treating the injured and providing emergency care. The most seriously injured sailor needed to be evacuated to a shore hospital for advanced treatment. The incident also caused significant material damage. The snapped cable sent metal fragments flying across the deck, damaging several parked planes and their sensitive electronics, which required extensive repairs. The arresting gear system was also heavily damaged, and the failed cable and its machinery had to be completely replaced, which was a complicated and time-consuming process. This led to a temporary halt in flight operations, affecting the carrier's readiness. The financial impact was substantial, with initial damage estimates in the millions of dollars. This figure did not include the cost of medical care for the injured sailors or the operational impact of halting flight activities. The incident had a lasting effect on the crew's mental well-being. Many who saw the close call felt more anxious during later flight operations. The Eisenhower incident was a strong reminder of how dangerous carrier operations can be and why proper maintenance and training are so important. It led to a full review of the arresting gear systems and procedures across the fleet, bringing significant changes to how these essential parts are maintained and operated. The investigation that followed uncovered several factors that contributed to the near disaster. The main issue was a maintenance mistake. The hydraulic system that controls the tension of the arresting cable was not adjusted correctly. This small error caused the cable to overtension during the Hawkeye's landing, leading to its failure. The investigation also pointed out that the maintenance procedures were too complicated, making it hard for sailors to perform the necessary checks and adjustments properly. As a result, the Navy reevaluated its training programs and maintenance practices across the fleet. The investigation's recommendations included simplifying maintenance tasks, improving training for arresting gear technicians, and introducing stricter quality control measures. The incident was a clear reminder that even small mistakes can have serious consequences in the high-pressure world of carrier aviation. Most importantly, the necessity of a perfectly functioning arresting gear on an aircraft carrier and double-checking to ensure everything was in perfect order before an operation was more understood in this close call. An arresting gear, also known as arrestor gear, is a mechanical system that quickly slows down an aircraft when it lands. This system is vital for naval aviation on aircraft carriers, especially those using catabar and stowbar systems. Similar systems are also used at land-based airfields for emergencies. The typical arresting gear includes several steel cables stretched across the landing area, which the aircraft's tailhook catches. When the tailhook grabs a cable, the aircraft's speed is absorbed by hydraulic systems below the carrier deck. There are also other systems that use nets, called barricades or barriers, to catch the aircraft's wings or landing gear in emergencies when the tailhook doesn't work. The concept of arresting gear dates back to the early days of naval aviation, evolving from rudimentary beginnings to the sophisticated systems we see today. This journey mirrors the rapid advancement of aviation technology throughout the 20th century and into the 21st. Arresting cable systems were invented by Hugh Robinson and were first used by Eugene Ely during his historic landing on a ship, the armored cruiser USS Pennsylvania, on January 18, 1911. In these early systems, cables ran through pulleys and were attached to heavy weights like sandbags. Later, in June 1931, more advanced arresting cables were tested on the HMS Courageous, designed by Commander C.C. Mitchell. Today, modern U.S. Navy aircraft carriers use the Mark 7 Mod 3 arresting gear. This system can stop a 50,000-pound aircraft moving at 130 knots in just 344 feet within 2 seconds. The system is built to handle a maximum energy absorption of 47.5 million foot-pounds at full cable extension. Before angled flight decks were introduced, 2 additional systems were used along with deck cables to prevent landing aircraft from hitting parked planes: the barrier and the barricade. If an aircraft's tailhook didn't catch a cable, its landing gear would be stopped by a 3 to 4 foot high net called the barrier. If the tailhook caught a wire, the barrier could be quickly lowered so the aircraft could taxi over it. The final safety measure was the barricade, a large 15-foot high net that stopped planes from crashing into others parked at the front of the deck. Barriers are no longer used, though ground-based arresting gear is sometimes called barriers. Barricades are still in use on carriers, but they are only set up and used in emergencies. In the 1920s, when aircraft carriers were still in their infancy, landing on these floating airfields was a perilous endeavor. The first arresting systems were scarcely primitive by modern standards. Sandbags connected to ropes stretched across the deck were among the earliest attempts to slow down landing aircraft. Pilots would aim to snag these ropes with hooks attached to their planes, relying on the weight and drag of the sandbags to bring them to a stop. This method was unpredictable at best and often resulted in damage to the aircraft. As planes became faster and heavier, more sophisticated methods emerged. The 1930s saw the induction of hydraulic systems, marking a significant leap forward in arresting technology. These early hydraulic arresters used pistons filled with oil to absorb the energy of a landing aircraft more consistently and safely than the sandbag method. The Second World War brought rapid advancements in both aircraft and carrier design, necessitating further evolution of arresting gear. The introduction of jet aircraft in the late 1940s presented new challenges. Jets approached at much higher speeds and had different weight distributions compared to propeller-driven planes, requiring arresting systems to handle greater forces. The Vietnam War era saw further refinements, including improved wire materials and more sophisticated control systems. The introduction of digital computers in the 1970s and 80s allowed for more precise control and monitoring of arresting gear performance. An often overlooked aspect of arresting gear history is its impact on carrier design. The angled flight deck, introduced in the 1950s, was a revolutionary change partly driven by the need for more efficient and safer arrested landings. This design allowed for simultaneous takeoffs and landings, greatly increasing a carrier's operational tempo. Interestingly, the development of arresting gear has not been limited to carriers. Land-based arresting systems have been developed for use at airports near bodies of water or in other challenging environments. These systems, while different in design, owe much to the innovations driven by naval aviation. On modern aircraft carriers, there are usually 3 or 4 arresting cables laid across the deck. Pilots aim for a specific cable to ensure a safe landing. They approach the deck at about 85% of full throttle, ready to power up if something goes wrong. If the aircraft successfully catches the cable, the engine power automatically reduces, but the pilot can override this if needed. If the aircraft misses all the cables, a situation known as a bolter, it has enough power to take off again and make another attempt. After a successful stop, the pilot reduces the engine power, raises the hook, and taxis away, clearing the deck for the next plane. These systems are not only found on carriers, but also at land-based military airfields, where they are used in emergencies or on short runways. Some airfields have backup systems with elastic nets called barriers that catch an aircraft's wings or fuselage, using heavy chains or other methods to bring it to a stop. In places with limited space, special concrete blocks called EMAS are used to slow down planes by crushing under their weight, making sure that every landing ends safely. The idea of stopping planes with cables and barriers first appeared during the Korean War when jet fighters had to land on short, unforgiving airstrips. Adapted from systems used on aircraft carriers, these early barriers used ship anchor chains to bring planes to a halt, preventing them from overshooting the runway. The main parts of an arresting gear system include the hook cables, purchase cables, sheaves, and arresting engines. The cross-deck pendants, also called arresting cables or wires, are strong, flexible steel cables stretched across the landing area to catch the arresting hook of incoming aircraft. On aircraft carriers, there are usually 3 or 4 of these cables. On U.S. carriers, these cables are replaced after every 125 landings to ensure safety. During aircraft recoveries, individual cables might be temporarily removed for maintenance on other parts of the arresting gear system. To make sure the tailhook can catch the cable, wire supports lift the deck pendants slightly off the surface. On carriers, these supports are curved steel springs that can bend when aircraft taxi over them, while on land-based systems, rubber supports lift the cables off the runway surface. Purchase cables, which look similar to arresting cables but are much longer, connect the arresting wire to the arresting gear engines. When an aircraft engages the deck pendant, the purchase cable transmits the force of the landing to the arresting engine. These cables are securely attached to the arresting wire using a heated zinc loop, although this process is risky, and the U.S. Navy is working on safer methods. In the late 1950s, the idea of using a piston pulled through a water-filled tube as a low-cost arresting system for land air bases was introduced. By the early 1960s, the British developed a more advanced spray-type arrest gear system for both land and sea use. This system used hydraulic cylinders moving through a water-filled pipe, with a smaller pipe alongside it that had holes of various sizes. The Royal Navy claimed this system had no weight limit, but there was a speed limit. On land-based systems, there are usually 2 arresting engines on either side of the runway. These engines apply braking force to the reels holding the cables or tapes, slowing down and stopping the aircraft. The 2 most common methods used are rotary friction brakes, which use hydraulic pumps, and rotary hydraulic systems, where a turbine inside a water glycol mixture creates resistance to stop the aircraft. After the aircraft is released from the cable, the tapes and cable are retracted by an engine or motor in the arresting engine. If there's too much runout during an arrestment, known as a tube lock, it could be due to improper settings, excess weight, too much speed, or too much thrust. Off-center landings can also damage the arresting gear. The new Advanced Arresting Gear System, or AAG, on American aircraft carriers uses electromagnets instead of hydraulics to slow and stop landing aircraft. This new system is more flexible, safer, and more reliable, requiring less maintenance and fewer crew members. It is particularly beneficial for capturing unmanned aerial vehicles, which are too light for the old hydraulic system. The AAG system is being tested on the USS Gerald R. Ford and will be installed on all carriers of that class. In emergencies, when a normal arrest is not possible, a barricade system is used. This system is usually stowed, but can be set up in under 3 minutes by a trained crew. The barricade is a web of straps stretched across the flight deck. When an aircraft engages the barricade, the energy is transferred from the webbing through the cables to the arresting engine. After use, the barricade webbing and cables are discarded, and the system is reset. Barricade engagements are rare since tail hooks are very reliable, and severely damaged aircraft might not be able to land safely. This system is installed on all American aircraft carriers and on the French carrier Charles de Gaulle. Aircraft carriers also employ multiple layers of redundancy to mitigate the risks associated with arresting gear failures. The typical configuration of 4 arresting wires across the landing area provides pilots with multiple opportunities for a successful catch. If one cable fails or is missed, the others stand ready to perform their critical function. Beyond the primary arresting gear, carriers are equipped with emergency barricades. These heavy-duty nets can be raised to catch an aircraft unable to engage the standard arresting wires. While rarely deployed, their presence provides an additional safety net for extreme situations. The flight deck of an aircraft carrier is often called one of the most dangerous workplaces in the world. To work safely in this high-risk environment, crew members go through extensive training and follow strict rules. Each crew member has a specific role during flight operations, and they wear different colored jerseys to show what they do. Yellow for aircraft handlers, blue for plane captains, green for catapult and arresting gear crews, and so on. This color coding system helps everyone know who is doing what, making it easier to work together quickly and avoid confusion in the fast-paced, noisy deck environment. Crew members also train regularly for emergencies, practicing how to handle equipment failures, fires, and aircraft issues. This kind of preparation proved crucial during the Eisenhower incident when the deck crew quickly took control of the situation and helped the injured, preventing things from getting worse. Pilots also undergo similarly intense training. They practice landing on the deck using simulators that can create different types of emergency scenarios. For example, they learn how to respond to a bolter, which happens when an aircraft misses all the arresting wires and has to take off again quickly. The successful recovery of the E-2C Hawkeye crew during the 2016 incident showed just how effective this rigorous training can be. After incidents like the Eisenhower cable break, the Navy has invested in better arresting gear technology. Today's cables are made from stronger, more durable materials that can signal when they're starting to wear out. Maintenance practices have also improved, with modern arresting gear systems featuring advanced diagnostic tools that monitor cable tension, wear patterns, and other key factors in real time. This allows for maintenance to be done before any problems become serious. The future of arresting gear technology is closely tied to the development of new aircraft types. With the advent of unmanned aerial vehicles and potential future developments like hypersonic aircraft, arresting systems will need to continue evolving to meet new challenges. Despite all these advancements, the fundamental principle remains unchanged: transform the kinetic energy of a landing aircraft into a controlled, safe stop. The most important technological advancement is the new advanced arresting gear system on Ford-class carriers. This system uses electric motors and energy-absorbing water turbines instead of the old hydraulic engines. The AAG is more reliable, needs less maintenance, and can handle a wider range of aircraft weights and landing speeds. While these advancements make carrier aviation safer, they also bring new challenges. As the systems become more complex, it's more important than ever to ensure that crew members are well trained to operate and maintain them effectively. Thanks for watching. While you are still here, click on the link appearing on your screen to check out another of our videos. See you there!